Good evening, everybody, and thank you for joining us for tonight's session or webinar on investigations involving derivatives. We're glad to have Dee Dee Stanfield with us, one of our advisory teachers out of Alabama. She has taught for 21 years, just about everything from 8th grade math up through calculus, and she's been using our graphing calculators for a long time. We are glad to have her with us, and without further ado, I'm sorry, I was about to hand it over to Dee Dee, but I do want to remind everybody, as usual in our webinars, audio is muted, and if you have any questions, you need to type them in the question pane, just for the sake of audio quality. And now, I will hand it over to Dee Dee.
Hello. Thank you. Tonight I'm excited about sharing with you some investigations that I have found helpful in my calculus class. I've taught AP Calculus for going on about 13 years, and I've been using Casio graphing calculators since I began teaching that. So we're going to just get started. You can see on my first slide, this is just a little snapshot of some interesting things that you can do with your screenshots for investigating derivatives and second derivatives. We're going to be navigating through many different screens tonight, many of the different icons on the Casio Prism calculator. We'll be using everything from the run matrix to the table mode. We'll be using graph mode a lot. We'll also explore the geometry mode tonight, and I think that covers about all the modes I'm planning on speaking on tonight. The first thing we're going to do is an activity involving evaluating limits. And before we actually do the problems where we look at the activity, I want us to think about the formal definition again of what a limit is. You know, a limit is if f of x becomes arbitrarily close to a unique number L as x approaches c from either side, then the limit of f of x as x approaches c is L. And this is written as the limit as x approaches c equals L.
Dee Dee, I'm sorry to interrupt.
Okay.
I'm sorry, I can't see your screen. I think you need
can't see my screen.
to
Let's start over then.
Yeah, since I'm sorry,
I was all over the place too.
Yeah, let's
all right, show your screen. People are right. Okay, I need to click on the show your screen button right there.
Yeah.
Okay, you want to start us over again?
Yeah, sure. Well, good evening, everybody, and thank you for joining us for tonight's webinar on investigations involving derivatives. We're glad to have Dee Dee Stanfield with us. She is one of our advisory teachers out of Alabama. She's been teaching for over 20 years and is very familiar with our graphing calculators, and I always enjoy watching what she has a chance to put together. So without any further ado, I will hand control over to Dee Dee, and she can get started. There you go, Dee Dee. You just need to
click on show my screen.
Share your screen with us, and we'll be all set.
All right. It's good evening. It's nice to be with y'all tonight. I'm excited about sharing some investigations that I have used in my own calculus class and pre-calculus class over the last few years. I've been using the Casio graphing calculators since I began teaching calculus, which was over 13 years ago, and used them in my algebra classes even prior to that. So I'm a real big
I'm not seeing your screen.
Oh no, and I clicked on show my screen that time.
Let's try one more time.
No one sees your screen. Okay, where do I click on?
Try that little triangle right there.
Okay, triangle.
I think show my screen or.
Okay, no one can see your screen. Click to start screen sharing. I'm clicking on it. It's not coming through to me.
I'm not seeing it.
Okay.
What in the world? Okay, it's like it won't do it when we're official. It'll only do it when we're talking.
Okay. So it's not doing it now.
I'm still not seeing it. Change presenter. You're the presenter.
People can hear you. Click to mute yourself. Hide control panel. No one can see your screen. Click to start screen sharing. And when I click on it, nothing's happening.
Okay, let me see something. It says you have control. Okay, let's see. Right underneath the little.
Now it's showing screen. For some reason, it just came on. Is it showing my screen now?
No.
Okay, the little box was gray. Now it turned green, and it's saying people can see your screen. Click to stop screen sharing.
What in the world? Try turning it off and turn it back on.
All right, turn it off, turn it back on. You see an on arrow?
Now I'm seeing it.
Okay.
Now I'm seeing it. So here's what I'm going to do.
Okay.
I'm going to start recording while this is showing. So your
Okay.
screen is showing. I'm not even going to bother with my own screen.
You want me just to go back and start at my own introduction? I can do that.
Uh,
Or are we good with that?
you know what? Let's just do that. I'm going to stop the recording.
Okay.
I'm going to start it up again. I'll introduce you, but it'll all be your screen so we don't have to mess with whatever weirdness is going on. You know, I don't know what's going on, but this just happened the other, not this exact issue, but something funny happened the other day with Mike Reiners too. So I'm wondering if there's a glitch with their software.
Okay, well good.
So,
maybe it's...
So it's not just us.
All right.
Well, good evening, everybody, and thank you for joining us for some investigations into derivatives this evening with Dee Dee Stanfield, one of our advisory teachers out of Alabama. We are glad to have Dee Dee with us. She's been using our calculators for a number of years, and I'm looking forward to hearing what she has to share with us this evening. If you have any questions, be sure to type them in the question panel as we have you muted for audio quality. So anyway, here you go, Dee Dee. It's all yours.
Okay, thank you, Nathan. I'm glad to be with y'all tonight. We're going to explore some calculus investigations that I have used over my years in teaching AP Cal, and also I use these in my pre-calculus class, and I hope you find something useful that you can enjoy. We're going to be using the Casio Prism tonight, and before we actually get started, I want to talk about navigating it. When you have your Casio Prism turned on, you're going to want to press the main menu button to see all the different modes that we can explore. Some of the things we're going to do tonight will involve the run matrix, the table mode, the graph mode, and we will even drop down and do one thing out of the geometry mode tonight, just to see, just a big, broad, selection of the things you can do with the Prism. Our first activity is going to involve investigating limits, and before we actually do the limits, I want to review the formal definition of what a limit actually is. If f of x becomes arbitrarily close to a unique number L as x approaches c from either side, then the limit of f of x as x approaches c is L. And the reason I really went over this formal definition tonight is because we're going to be looking at a lot of problems numerically, graphically, analytically, and when we come to some limits that fail, we need to really know that definition so we can see what part of the definition is not being met so that we understand the reason the limit doesn't exist. So our first problem we're going to investigate is to investigate the limit as x approaches 3 of 2x minus 4. We want to create a table for the function y equals 2x minus 4 using the Prism, and we're going to notice the value that x approaches. Okay, so I'm going to swap this over now and pull up my calculator so that we can explore some things on the calculator. Well, first of all, we're going to go to our menu. And on your main menu for right now, we want to go to the table mode because we're going to type in a function into the table and just basically let it compute some values for us. In my table mode right now, you can see I was previously working on another problem, so I need to delete my screen so it'll be cleaned up for our investigation. So if you're having trouble delete, you press F2, then F1, and that sets your table to an empty screen. Now the function that we were investigating was 2x minus 4. Remember to always use this key for your variable when you're putting in. And if you notice, I put 22 instead of 2. So I need to back up to that 2 that I want to delete and delete it out. It's real easy to back it up and correct your mistakes before you move on. In order to produce the table, we need to store it first by pressing execute. And then we want to set our values. We want to set this table up from a, for a specific range so that we can especially investigate the values as they approach 3. And in order to investigate what's happening at 3, let's first start with maybe 2 as our start value, and let's end it one step past 3, such as 4, and maybe investigate it in increments of a tenth, just to kind of see a picture in general of what's happening. You see that when x is 2, you've got your corresponding y value. You've also got a table. I've got my derivative feature turned on, but we're going to try to just ignore that column for right now. But we're going from 2 all the way to 2.5 to 3, all the way, the values are listed all the way up to 4. But specifically tonight, we're wanting to investigate what's happening as x approaches 3. And from our values here in the table, we can see it's at 2. If we wanted to really zoom in very close to 3 and start off with some values that are a little closer than just 2.9, we can come back to our table and replace the 3 with a number even closer to 3 than 2.9, such as 2.99. You can enter that value and immediately it changes the ordered pair you had in, and now you see the corresponding y value. I want to get even closer. I want to investigate what the value of 2.999 is. And you can see as we're doing this and getting closer and closer to plugging in the actual number 3, our values were getting closer and closer till it actually became 2. If we go on past 3 and come toward there, if we were on graph paper, we're actually approaching 3 now from the right side. We could plug in 3.001 so that we're the same distance on the right side of 3 as we were earlier with 2.99. And you can see as we went right past where we've entered x is 3 and got 2, we're now getting a y coordinate that's a little bit more than 2. We can continue this pattern and plug in 3.001, and you're going to see the values gradually creep away. That we had 1 decimal too many. Let me change that to 3.01. We're seeing our values for y gradually grow further and further away from where we were at 2. We can go to 3.1. Now from this, if I go back to the thing, to my PowerPoint here, we can create a table. If we had given students a blank table and asked them to input these values, they can investigate the values of a table real easily using the Prism. The next thing we'd want to do, though, to really get an idea of how this numeric data fits to a graph is actually analyze the graph. So let's go back to our calculator again, and now we're going to move to the menu, go back to your menu, and move over to the graph mode. And what's nice about this is if you've input a function into your table, it's going to be carried over to your graph function without you having to input it. So it's going to graph what you were just analyzing in your table. And we can adjust our view. Let's adjust the view window before we actually produce the graph. And that's one of the neat features on the Casio, is that the view windows are real easy to set. If you want just a nice, clear, nice view window, press F1 so that your view window is set to a screen that'll make the graph appear real square. And we're going to press Exit now to take us back to that screen. And one more thing I want you to do, if you've just gotten a Prism or learning how to use it, we're going to go to Shift and to Setup so that we can look at the different options that are available for our graph grid. One of the things I want us to make sure tonight is that where it says Grid, that you've got your line zone tonight, and under Axes you've got your scale factor on, so that when we produce a graph, which we're going to do by clicking the blue Execute button twice, you not only have a nice graph, but you've got your grid lines and you see the scale on it. Now remember, our investigation for this problem was to see the limit, which is the value as x is approaching 3 from either side, is the y value, this coming to the same y value. And we can check this by tracing the graph. If we trace the graph by using our arrow key, we can just follow it until we are actually where the x coordinate is 3. And if we want to mark that point, we can press Execute. And if you press Exit and then regraph it, you can still see that ordered pair marked, showing you that definitely there is an ordered pair on this graph at 3, 2. Now, when we're talking about polynomials, such as this linear example, you're going to realize that limits can always be found through direct substitution. Look back at the problem and you see that we could have just plugged 3 into our function and had 2 times 3 minus 4, and we would have had the same value of 2 through direct substitution. But not all problems are going to be quite that easy. So the next problem we're going to look at is one that presents a little bit of a problem. If you evaluate this through direct substitution, think about what you would get. You would realize real quickly that through direct substitution you have 0 in the numerator, which is okay, but 0 in the denominator is not. And when you have a problem in the form 0 over 0, your graph has got a point where it's not continuous. It's got a point of discontinuity, and you can see that if you use your table feature, you're going to get error at 0. Now this is the table, and these are the values that you'll get, but I want us to investigate the how to input this in the table mode. That's another one of the features that really impressed me when I first started using the Prism when it came out about a year and a half ago, was the fact that it has the natural text display. If I want to input a fraction, I'm going to use my fraction key, and in the numerator I'm going to use my variable key to input the x. In the denominator I'm going to press square root, and to get to the square root function you realize it's above the x squared, so Shift and x squared gets that into the problem, and now use your variable key again. The function was x plus 1, and now I'm under the radical right now, and you can see as long as that cursor is blinking under the radical, that's where I'll be. To move out from under the radical, I need to move the arrow key over once, and now put -1, and that's the function we were dealing with. Now we were investigating this particular limit as it approached 0. So I need to go back and set my parameters so that I'm approaching 0. And I think right now one good thing probably to do would be to start at -0.1, and let's end it at +0.1, and let's use increment steps of 0.1 and just kind of begin by looking at that. If you look at your table now with these values, you see real quickly that from -0.1 we had a value of 1.946, but 0 produced an error. But the moment we were past 0 at 0.1, it appears that we have values of 2. Well, I need to zoom in a little more between -0.1 and 0 to 0.1 just to be sure. So we need to exit and go back to our set, and we're going to set this up. And what I'm going to do is I'm going to keep the -0.1 as it is in the 0.1, but I want to change this so that maybe I'm looking at it in steps of 0.001. In other words, 1/1000th of a step. So now let's go back to our table of values and let's look and see what's happening here. Well, we've got -0.1, but I want to change this. I want to let this be -0.01. That's a little further out than we were before, or closer in. Excuse me, I clicked the graph mode. Okay, now what I want to do is type in -0.1. I'm sorry, I'm typing in the wrong thing. I wanted to go -0.001 because we're really getting close to 0. And then I want to type in -0.0001. So we're really getting values that are so close to being 0 that we're seeing this get really infinitely close to 2. And if we move the arrow key over to that number, it shows you in the table the number rounded to 4 decimal places, but when you cursor over to it, you see the number down here has the value of 1.9994999. Okay, let's recall what 0 gave us. If we go back to our X column and enter 0, we'll see again that that's still producing an error. Well, let's get infinitely close to 0, or as close as we can. Sometimes in Alabama we call this getting dang close to 0. We're going to go 0.0001 on the positive side. And again, you see that we're getting a value here that's, well, it's actually showing me 2, but we really need it to be close to 2. So let's come back and say 0.001. And there we are. It's 2.004. So we're really close. And if we type in 0.01, we're getting a little further away. You can see we're growing away from 2. Again, let's go investigate this by looking at the graph. Sometimes, it's nice to look at tabular data, but until you look at the graph, you really can't visually see what's happening. So here we are again. We're at our graph mode by just, going to the graph. The function's already carried over. You can either press F6 to graph it, or you can press the execute key, and there's a graph. Now, if you were a student and you just graphed this and you didn't look at the table, you might not notice that that there's a problem when x is 0. We really can't see that there's a problem. So what we're going to do is we're going to trace this, and you see immediately when you press trace, it's going to take you to where the x coordinate is 0. And right now, when your x coordinate is 0, your y value is an error. My derivative feature also says it's an error, and that'll make more sense to you in a later investigation when you start doing derivatives. But you can see as we toggled to the left, we were approaching values that were getting infinitely close to 2, but it was actually undefined there, and when you go to the right, it grew past 2. What we can do to make students really understand that there's a point missing, maybe if you're making a test and you want to use your emulator software to create a test, or you want to just help students really see what's going on. Under Sketch, under F4, we can go over to where it says Circle, and we're going to carry this arrow up here to where we would like a little bitty circle. I'm going to toggle it just barely to the left and press Execute, and then I'm going to toggle it to the right so that I can create a circle right there. Now when I press Exit and regraph it, that kind of helps me mark a point and know that right there is where I was really trying to notice that there was a point of discontinuity. So when we go back now, what would that mean about our limit? Well, that would indicate to us that when we're at 0, we don't have a value there, it's undefined, but the limit is actually approached 2. So the next thing we want to investigate is look at some limits that actually fail to exist. And we'll be using our table. We'll look at tables and graphs again to explore unbounded behavior. The first graph we're going to look at is f of x equals 1 over x squared. And I want us just to look at the graph first and think about where this function is undefined, and that might give us an idea where the limit will fail to exist. So again, I'm pulling up my calculator. I'm going to press Exit just to take me back to this graph mode screen. Delete the original function. You've got your fraction with 1 in the numerator and x squared in the denominator. And now we're going to graph it. Well, we can see that it appears as we travel to the left, the graph is getting flat. It's approaching the x-axis, and on the right side it's doing the same thing. But what is it doing as it goes up? You know, it might be one of those graphs that comes up, makes kind of a parabolic kind of arch turn and comes back down. It could, you know, who knows, it might have a cusp in it. I really can't tell just from this view window. I could press the arrow key up and I could see a little more of the graph, but I still am not, you know, convinced that there's absolutely not a point up here where this is turning and coming back down. Well, what I can do then in order to try to determine that is I'm going to press GSolve and I'm going to press max, because if it's got a max, it would take it to it, and obviously this one apparently is growing without bound, because when I press maximum under GSolve it says not found. So that indicates to me that I know a little something about this graph, that it's going on forever in the vertical direction on both sides. Okay, well, so that kind of helps me know that this graph does not exist because both sides are approaching infinity. And if you recall our formal definition again, the formal definition said if f of x becomes arbitrarily close to a unique number L, we didn't approach a unique number L because we were approaching positive infinity on both sides. So that is why this limit actually fails to exist. Okay, the next kind of limit we're going to investigate is one that has left and right hand behavior. So in order to investigate this, we want to graph it, and we want to ask ourselves, look at the graph and say, what did the graph appear to be approaching from the left? What did the graph appear to be approaching from the right? And then we want to recall our definition again. Remember our definition. The formal definition says if f of x becomes arbitrarily close to a unique number L as x approaches c from either side, then the limit of f of x as x approaches c is L. I believe it's real important for us to keep re-emphasizing the formal derivative definition every time it fails to exist, so they really memorize that definition. Well, when we come back to this graph, this is one of the neat things that's fun to do as far as absolute value on the calculator. We can press our fraction button, and I want to have the absolute value of x up here. So since I don't see absolute value on a key or above a key, I'm going to press options, because if you don't see something obvious, check it out in your option button. And under option, we've got calculus options, we've got probability, we've got all kinds of different things. But this is a numeric option. We're going to press F5 for numeric, and then F1 because that corresponds with absolute value on your soft key. Press your variable x, and then in the denominator, you're also going to have another x. Most of you are probably familiar with what this graph looks like. Uh-oh, we were graphing something earlier. I don't see anything else. I want to push the down key, oh, there it is. we do have more graphs. Sometimes we have to just shift our viewing window around so that we can actually investigate everything and not leave something out. Now, if I just looked at this graph, I would, think if I trace it, that on the left side, I can see every x-coordinate has a y value of -1. But the moment I becomes 0, it says error, which tells me that there has to be a point of discontinuity or a point that does not exist. This line was infinitely close to being x equals 0, but the moment I was at 0, it does not have a defined point. If I keep moving to the right, I'm immediately transferred up to this upper line. And on this line, as you go across, you see that all the y values are 1. Again, in order to really emphasize that this graph made a jump from here to here, it might help your students if you come back and draw some little circles there to really emphasize that, so that they can see that this is a place where the graph was undefined. We press the execute key, that starts my circle. I shift it over just a step and then press execute again, and that way I have a circle left in place. I'm going to do the same thing up here. I'm going to go over, press execute. I've drawn another circle. I want to exit out and come back just so that I can see my graph. I like to right click on graphs like this sometimes, and I can just copy them quickly and paste them to a Word document, and it's a great tool for building tests. Okay, so coming back to this problem, we have a limit coming from the left that's okay. The left-hand limit is -1. I have a right-hand limit coming from the right. I can say I am approaching a value of 1. But from our formal definition, remember what it says, that they have to approach the same unique number, L, and they didn't here. So again, this is another example of why the derivative fails to exist. Our definition of a derivative is built off of the limits, off of a limit. So that's why I wanted us to investigate some limits before we actually jumped into derivatives tonight. Our limit definition for a derivative says that as h approaches 0, the difference quotient between f of x plus h minus f of x over h actually gives us our derivative. And most of you know that sometimes is a difficult concept for students to kind of grasp and visualize. And we're going to go through an activity. This can also be found in the Calculus AP exam study guidebook that was written by Mike Reiners and Jan Borg, and you can find it, I believe, online. There's a lot of great AP Calculus activities. This one's going to be an investigation that helps you see that the secant line actually can become the tangent line. To do this activity, we're going to pull up our graphing calculator and go back to the main menu and actually enter the geometry mode this time. So I'm going to press exit, and I'm going to go to the geometry mode, which is in the lower left-hand corner. You may have something, your calculator may be new, or you may have something there already. We're going to start from scratch. So press Option, and when you press Option, we're going to press F1, and under the geometry mode, it's going to let you do sketches, it's going to let you do dilations, you can import backgrounds, pre-stored pictures, but tonight we're going to open up a new file and sketch our own picture. So press Execute to open up a new file. I do want to clear the current image, so I'm going to press F1. And while we're doing this, I want us to talk about the different things that F buttons do under geometry mode. F1 is where you go to open new files. You can right-click over and you can see the different views that you can pull from that F1 button. F2 is your edit button. That's where you're going to undo, select all, deselect, clear. F3 is where you actually use this feature for drawing point lines, all kinds of geometric figures. Draw Special, this is where you can pull up triangles and isosceles triangles and different shapes. F4, this is what you would use if you were doing constructions of different kinds of segments. F5 is your transformation tab, and F6 is where you go to do animations. Well, what we're going to use right now is the F3. We're going to be drawing. We're going to go to right arrow over to Draw Special. And the special thing that we're going to draw right now is we're going to use the function builder, the f of x, which is number 7. We're going to execute to enter that. And the actual function that we're going to enter tonight is kind of a complicated function. It's going to be 2 sine, using your parenthesis twice. We're going to have a color matched parentheses so that we know which parenthesis goes with what. We want to hit shift and pi, so press the bottom key down here to get pi. Divide it by 3. Close that parenthesis, and then place your variable in x. Close your parenthesis with a blue parenthesis. So now you know that this set of parentheses corresponds with this amount, this quantity, and the blue parentheses corresponds to the whole argument of the problem. Now once you've entered that, we're going to press execute to actually graph it. And once you do that, you're going to have to use your mouse pad to kind of move your pink arrow off your graph, but then you see you've got a solid black graph. Now before we move on, we want to adjust our settings again. So anytime you want to adjust your setup, you press shift and setup no matter what menu you're in. We do want our angle to be in degrees, and it should be. That's like the default. This always goes back to this setting. But under grid, we want to see some graph paper. So we're going to set our grids to have lines. The grid space is going to be scaled by 1, so we could change that if we wanted to, but 1's good for this one. And I do want to see my scale. So under axis, turn on your scale, and now press exit. And now you have your graph with actual grid and scales on it. Now I need to move my pink mouse back to my graph. And you know, one of the nice places on the graph is actually right here at the origin. If I press 5 on my keypad, it's always going to take me to the center of my graph. So now that that's there, notice how your graph is blinking and it's in yellow, and that's good. We're going to want to select a point and draw on it an infinite line from that point to another point. So while that's blinking, you need to enter the draw menu again, which is F3. And under F3, we're going to go back to draw instead of draw special and go down to infinite line. Select infinite line, and while this is blinking right there, go ahead and select it, or while it was pointed there, select it, and now arrow over with your arrow. And I want you to come to where X is 2, and then go up where X is about 2, as close as you can get it, till it's on the other graph again, and I want you to select that point. Now we've got a line drawn through there. Now in order to see this better, I'm going to arrow down so that I can see definitely that I have a line drawn through my curve. Right now we consider this line to be a secant line to the curve. The next thing we want to do in order to create an animation is to go back now. I'm going to press 5 again to take me back to my graph, the center of it, and I want to scroll up until my yellow graph is blinking. So I want to select this graph again. Let's see, I tell you what, let's go back to 5 again. Just select it there and press execute. Okay, and now we're going to come on up to the black graph again till it, to the cosine, the sine graph, till it's in yellow, so it knows we're pointing to it, and we're going to select it. Let's see, hold on a minute, I'm having a little difficulty here. I want to come back to, I know what I did. Okay, here we are. We need to be there and select that point, and then come to my yellow line and select it. I may have over-selected here. Let me clean this up just a minute. Let's go back to F2, and what I need to do is to deselect all. If you ever do select more than you need, just you can come back and just press clear all or deselect all and just start it back over. Oh, I lost my graph, so that's no big deal. We're going to go to draw special, scroll down to your function. Again, this function that we typed in was 2 sine, 2 parentheses. We want to have our pi divided by 3, close the parenthesis, put your X in, store it. I'm going to try to go back through these directions kind of quickly, and if you ever want to really go back through this again, you can replay it and see the steps, or use the guide. That's a good thing too, to have it beside you when you're going over it. So right now we've got this graph, and we want to select the middle points. I'm going to go back to that middle, select it. Now I've got my graph in black, and I want to go to F3. I want to draw an infinite line from that point through my tree graph at the place where the x-coordinate is about to, all right, and then I need to come back to 5, and there I have it. I have my line drawn. Okay, and what I need to do now that I didn't do the first time, this is a very important thing, and I don't know why I didn't think to remind myself and you too, is to press exit. You want to press exit before you go on to the next thing. You always want to deselect before you try to start a new function. All right, now that we've got this drawn, I do want to come back now to 5, and I want to select that point, and I want to come back now to my to my graph and select it. And now that my graph is black, that's what I was trying to get to happen a little while ago and was having trouble. I'm going to press F6 to add an animation. So press execute, and now that I've got that pressed, I need to press F6 again to edit my animation. And I don't want it to repeat 10 times. I think for us 3 times is enough for it to repeat and see what's happening. I'm going to keep it at steps of 20. And I'm going to start it. Now, T sub 0 and this is more like a T sub 0 and T sub 1. This is the x coordinate I want my investigation to start on. I'm going to investigate it from 0 to 4. So I'm going to see this animation 3 times in increments of 20 steps from 0 to 4. All right, I'm going to now press F6. Let's see, let me press F6, and I want to go to 6 to repeat and see this animation. And now I can see the animation, and I basically did this so that we could see the secant line literally become the tangent line for the moment that the point B was on top of A. So when B, the horizontal distance closes in to where B is actually on A, it becomes a tangent line. So let me go back to our PowerPoint now, and let's think about what we should have gotten from this investigation. From this graphical exploration, you want students to see that as the distance between the x-coordinates lessens, the points and the curves get closer together. You want them to understand that the secant line becomes a tangent line when the distance between the x-coordinates becomes 0. Ultimately, you want students to understand that the slope of the secant line, which is always found by the difference in y over difference in x, in terms of function notation, we change it from y's to f's, and then this is approximately going to give us, it's going to be equal to the limit as the x1 coordinate actually becomes the x2 value. In other words, that causes the denominator to be 0, so that we have that phenomena happening of it becoming the actual slope of the tangent line. So this kind of helps them progressively see and understand how that happens. Okay, the next slide we're going to look at is going to involve derivative behavior of functions. In pre-cal and in the beginning of calculus, I try to give them some lessons where they have to investigate derivatives, predict what the derivative rule is, and then they test it. And so that's what we're going to do. We're going to look at a bunch of functions. We're going to graph the function. We're going to graph the derivative using the derivative graph feature. We're going to see if we can figure out what the derivative is, type in that function, and then see if they correspond. The graphs we're going to explore are going to be that of f of x equals -2, 2x minus 3, x squared, -3x squared, 1/3 x cubed, and 2x squared minus 3x. So I'm going to be calling these out as we come across them, but I wanted you just to kind of have them all on one screen if you want to print the screen out later on. Okay, so now on our calculator, we're going back to the graph mode. We're going to really do some explorations. Graph mode is an excellent tool for investigating all kinds of calculus topics or any kind of algebra topics. Now, the first one I said we were going to test was -2. That's just the constant function. And before we go on, one of the nice things is that we can do multiple graphs, and they're each going to appear in a different color, and that makes it really easy when you're trying to compare them. In order to pull up a derivative of a graph, that is an option. I don't know if you remember earlier when we pressed option before how we saw calc as one of the options available. Well, we're going to use calc this time. When we press F2, we now see that we can do the first derivative or the second derivative. We're just going to investigate the first derivative right now. So I've got the first derivative, and in this box I want to pull up y1. So I use the soft key. There's my y. I press F1 to pull up function 1, and I press 1 so it knows I'm wanting to take the derivative of y1. We do not need to put anything in this box because we're not finding the value of the derivative at a point. We're actually graphing the derivative. Now when we graph this derivative, I want you to remember that the blue line was your original function. That was your y1. y2 was your derivative of this graph. Now when you look at this graph down here, the blue graph, I'm going to turn on my trace feature, and I have my derivative feature on too. You notice that along the blue line, no matter what x is, the y coordinate was staying constantly -2. You also see that my derivative here has a value of 0. What that means is that this graph's slope along every point is 0. The derivative is just the slope of the line, so the slope of the tangent line. So the slopes of the tangent line along this line are 0 at every point. That's why the derivative is actually, for every x coordinate, the y coordinate is 0. It's also a horizontal line. Now, what is the equation of this red line? Of course, it's y equals 0. Well, when we go back, now that we think we know that the derivative of -2 is actually y equals 0, let's type in 0 here and see if that does graph over what we think the derivative is. As we do some more complicated functions, this will make a little more sense. This is a very simple one. My derivative graph went on top of the red graph, so I know that that function, the equation of that line, is 0. Now, we're going to delete y3. I'm not going to mess with y2. I'm going to leave that as the derivative of whatever we put in for y1. We don't have to change that every time. Now, the next function we were going to investigate was 2x minus 3. So we're going to investigate 2x minus 3, which you know is just a straight line. It's a straight line, and it's passing through the x-axis at -3. Notice that this line always is going to have a positive slope of, what is the slope here? 1, 2, 2 over 1, so the slope of this line is 2. And notice what the derivative value is. My derivative for this problem is constantly always got a value of 2. The slope of this line is 2. The graph of this line is 2. Well, let's come back and look at this. So we now know that if y1 is 2x minus 3, its derivative happens to be 2. We think we can prove it by actually graphing y equals 2 and seeing, yes, y equals 2 is the derivative of this function. It's on top of that line. Well, we've investigated two linear situations, one that was the constant function, one that's a linear function. Let's now look at a function that's a little more complicated. Let's just use x squared. X squared is just a parabola that's going to be, the vertex is at 1. We know that the parabola comes down. On this side, we can also do another thing, which is sketch tangents. This might be helpful. We can look at the tangent slope along the side. When we were on the left side of the parabola, moving down toward the right, notice that all the derivative slopes were negative, and that's why the red graph is also negative. When the slopes of the tangent line are negative, the derivative would be negative in value. And as you move around till you get to the minimum point on the parabola, or the vertex point, notice that your derivative value is also 0, and that's where it corresponds to the graph at 0, 0. As you come up the right side of the graph, the tangents are positive, and the red line is now positive in value. Okay, I'm going to turn off my tangent line, my tangent sketcher, and let's focus on what is the equation of this red line. It's passing through the origin at 0, 0, so the y-intercept is 0. It has a slope of 2, so the equation of this red line should be 2x. Well, that means then that we have discovered that the derivative, if we're right, if it graphs out on top of the red line, then we will know that the derivative of x squared is 2x. So let's see if we're right by checking to see if that line graphed on top of the other line, and it did. So we're pretty sure we're catching on to maybe a rule. We're developing the idea behind the power rule. The next function we're going to explore, let's try -3x squared. -3x squared is a little different because it's negative in value. We know that's a parabola that's stretched vertically, and it's going downward. Notice the difference in my derivative graph this time. The parabola was increasing. It had positive slopes on the left, so my derivative is positive in value on the left. Right here where you had a horizontal tangent with a slope of 0, the derivative graph is 0. Where the derivative slopes, or the slopes of the tangent line would be negative, the derivative value is negative. And if we look at this graph, we know it's crossing the y-axis at 0, and I'm trying to see a nice place where it crosses so I can count the slope. I'm going to shift upward, so maybe I can count. From the origin, I can see still I've gone 1, 2, 3, up to 5. I'm going to go up one more click. Let's see, at 6, I see that I'm going up 6 before I make one step left. So that means that this equation, the graph should be negative 6x. Now really look at what we're saying. The function was negative 3x squared, and we're now saying the derivative is negative 6x. If we're correct, yes we are, because you see I graphed on top of it again, and I do want to go back and adjust my view window back to an initial screen so we can see that a little more clearly. So my derivative for negative 3x squared is negative 6x. All right, let's try it on another function. We've explored linear, we've explored quadratic. Now let's explore a cubic one. If we put in the fraction 1 in the numerator, third, 1/3, arrow over to get out of the denominator and press X, use this key to raise it to the 3rd power. Can you make a prediction? I would ask my students at this point, can you make a prediction of what you think the derivative might look like? We noticed that the constant function went to 0, a linear function went to a constant number, a quadratic equation went to a linear function. It seems like everything's kind of going down in power. So hopefully they have realized that since this is cubic, that the derivative will be quadratic. We'll go from a 3rd degree function to a 2nd degree function. And this is a parabola that passes through the origin, and it looks like it's passing through the points 1, 1 and negative 1, 1. So that should be the graph of just x squared. And we could investigate tangent slopes going up. This is positive, then it was 0 again. Then this graph was forever increasing. That's why the graph of its derivative is always in the positive range, except for where it had a horizontal tangent. So we think we know that this derivative is x squared. We test it by typing in x squared and seeing that it does graph on top of what the calculator had down as the derivative. Okay, we've looked at some polynomial type functions. Now let's look at some functions that are a little more complicated. The next one we're going to do is we're going to investigate the sine of x. The sine of x. And when we graph the sine of x and its derivative, you see something real familiar come up with it. The graph of blue is my sine of x, and if you notice when you look at the derivative graph of the sine of x, it appears to be the cosine of x. So maybe we've discovered the derivative rule for sine x. Let's type in cosine x and see if we're right. Yep, there it is. The cosine graph graphs right on top of the derivative of sine, so we can now say that the derivative of sine of x is cosine of x. Real quickly, let's explore what the graph of cosine x is. Maybe since sine was cosine, maybe cosine is sine. We'll have to just see. When we graph the cosine of x, we get, oh no, it's not the sine of x. It's not the sine of x, but it's the reflection of the sine of x over the x-axis, which makes that be negative sine x. So when we type in negative sine x and graph that, we can see for sure that we have proven that the derivative of cosine is negative sine x. Now the next one we're going to prove is just a little more difficult for students sometimes to understand, and that is the derivative of tangent x. When we graph tangent x and graph its derivative, it's a little different. It didn't just take it and turn it or something. It's an actual different look altogether. And most of your students, if by the time they're in pre-calc calculus, they have graphed tangent, they've graphed secant and cosecant and cotangent. So hopefully they're going to look at this and say, you know, this kind of looks like the secant graph, but all the secant pieces are all going up rather than one up, one down, one up, one down. And then you can have them think, well, what can you do to a function so that you make all of its y values always positive and not be negative? You might throw out something, just some minor examples just to kind of get them thinking about that. And so hopefully they're going to see that this is the secant of x. It is a little stretched, it's a little narrower than like a normal secant graph, but it is secant and secant, they're all positive. So hopefully if you kind of probe them and prod them in little ways, they're going to realize that that's the secant squared. Now you don't have a secant button on your calculator, but we can put our parentheses in and put a fraction in. Put 1 in the numerator. This is a good review of their trig identities. Put 1 over cosine if they've got to graph the secant, and we're going to try to square it and see if that does fit our graph. So we're predicting that the graph of tangent x is basically secant squared. And when we graph this, we're going to see that it is the case. The secant squared graph goes right over that, so we now know for a fact that the derivative of tangent is secant squared. We're going to look at one more before we leave this investigation activity, and that is going to be the graph of e to the x. Now, before we hit that execute key, I'm going to warn you, we've got to be real careful. I'm going to press it once, and then I'm going to press it twice, and it's going to happen so fast. If you're not watching the screen, you'll miss it. There it is. There it is. Did you see it? The graph of e to the x and the derivative of e to the x are exactly the same. So that must mean then that the derivative of e to the x is actually e to the x. Let's prove it. We're going to have a blue, a red, and then it's going to go green real quickly. Blue, red, green. So yeah, we're really right there. The derivative of e to the x is e to the x. By having them investigate and discover some of these rules on their own, it kind of helps them go back to their paper and pencil and be able to compute derivatives and remember the rules when they're on their own. The next thing we're going to look at are going to be some neat calculator active tips for taking derivatives. What I did was take just a couple of problems off of some old AP tests and kind of reword them in a way so that we could look at them and kind of explore what we would do with a calculator to make this be an easier problem. There was a problem one year that was stated similar to this. It said y equals x cubed plus 6x squared plus 7x minus 2 cosine x. Where would this graph change concavity? Now, you probably, by the time you get to the AP exam, you've had them do this by hand many times. Find the first derivative, find the second derivative, set the second derivative equal to 0. But what you want students to be able to do on the calculator part of the AP exam is know that if they're trying to find where the second derivative is equal to 0, then they can just graph the second derivative and quickly find the roots. So when I get to this point, when I start getting into review mode for the AP exam, I try to really show them neat ways to quickly get through the problems, because part of the AP exam challenge is taking the test in the length of time that's given. So let's input this function again. It was x to the third. Whoops, I'm sorry. Let me delete this out. There you go. X to the third. I need to arrow over to get out of the exponent's position and type in plus 6x squared plus 7x minus 2 cosine x. I didn't even take the time to find the first and second derivative by hand. I'm going to store that function, and now I'm going to go option, back to calculus again, this time to the second derivative, and I want to take the second derivative of my y1 function, and I'm not going to do it at any particular point. But what I do want to do, because I don't want to see the first derivative, the function itself, I'm going to hit select, and that will kind of deselect it. Only the equal signs that are colored are going to graph, and until you deselect it, it's automatically going to go and graph. I want to graph just the red graph, and I want to explore where it's crossing the x-axis. The quick way to find that root is to press F5 for GSolve, and when I press F5, I'm going to press F1. I don't have to select the upper and lower bound. It's just going to go right to my root. Now you notice that this root is at negative 1.89409. The values are down at the bottom. What if there's another root and it's just not visible on my view screen? You know, there might be. So what I need to do to check for any other roots is press the right arrow key over, and this little symbol means it's looking for another root to the right. Nothing came up, so that means there's not one. Press it to the left, and you can see there's not a root there either. So the only root of this problem is the one that was found initially. So that would be the answer to that problem. The next problem that I wanted us to look at is, given that the velocity is equal to t sine t squared, find the velocity and acceleration at t equals 1.5, and then determine is the speed increasing or decreasing at this time. In order to do this, we want to evaluate v at 1.5, and then we want to evaluate the acceleration, which is the derivative of the velocity, at 1.5 and compare signs. So let's go back to our calculator, and we're going to change modes. We're going to press menu, and we're going to go to our run matrix. We haven't really used this much tonight. So in my run matrix, I want to delete all that was previously there, and I want to type in, I want to evaluate that function that we had at 1.5. So we're typing in 1.5, that was the t value that we were evaluating, and we need to press the sign of parentheses. We're going to put 1.5, that's our argument, and we're squaring it. So 1.5 squared, and I'm just going to press execute, and that gives me the value. Now if you didn't get this answer, you may be in the wrong mode. You might be in degree mode. So always check and make sure that you're in radian mode. So when you press shift setup, scroll down to angle, and it's real easy to change from degree to radians or even gradients, but we want to be in radians. So if your answer wasn't right, that's what you needed to do. Now the next thing we needed to compute was the derivative at 1.5. So I'm going to press Option, and under this screen, Calculus options are above F4. I'm going to press F2 for derivative. My function was x sine of x squared, and this time I'm actually evaluating derivative at a specific point. So anytime you're evaluating something, you use the run menu. When I evaluate the derivative at this point, that tells me the acceleration is negative 2.0487. Now one of the big things that's been on almost every test I've ever been able to look at or get study guides for has always had the question of, is the speed increasing or decreasing? So from this screen they can real easily see that their velocity was positive while their acceleration was negative, so that indicates the speed is decreasing. There's always points on every test that involve that kind of problem. The last thing we're going to look at as far as quick problems is that if I gave you f of x is e to the x and g of x is natural log x and h of x is equal to f of x minus g of x, could you find the absolute maximum and minimum on the interval, the closed interval, from 0.5 to 1? In order to do this, we need to evaluate the intercepts of h of x's endpoints, and we could do the intercepts of h prime, but I'm going to do it a little differently than what I originally thought. We just want to evaluate this graph and find the max and min and evaluate the endpoints. So back to our graph grid again, our graph mode. We're going to press menu, go back to graph. I need to clear out this last stuff we were doing previously. We're not going to use a derivative feature at all now. We're going to use something else. The function that we're inputting is e to the x, so I'm going to press shift, my ln key, it's just to the variable x. Make sure you arrow position, subtract the natural log of x. I'm going to store that. I want to adjust my view window, I need to hit shift view window, and we were really wanting to see it between between 0.5 and 1. So instead of doing it at 0.5, I probably would go a little smaller than 0.5, like maybe 0.2. And I would want to go past 1 a little bit, maybe 1.2, and change my scale to 0.1, or to a tenth. Let's see if this is good for us. We're going to press execute and draw this. And right now I see my graphs, it's kind of off the screen a little higher than what I want to I want to see more of it. So press the up key, and that allows me to see more. And I really wanted to see the values at, what was it, 0.5. That was my endpoint. So I'm going to press trace and now press 0.5, and that automatically lets me enter the exact value that I wanted to evaluate. And you can see that comes up on the screen as an ordered pair. Press execute, and then let's go evaluate the other endpoint. We're going to look at 1. So visualize that the only thing you're wanting to do here, I'm going to press exit to get that cursor off, is look at the graph between these two endpoints. So try to get the students to realize we're just basically, if we could erase, we'd erase this segment and we'd erase this piece, and we're only looking at this graph from here to here. I can already tell that that's definitely my max, but I'm not sure if that's the min. This may have dropped down at some point lower than that. We could go back and address our y-axis and see a little differently, but the quickest way to find out the minimum would be to press F5 and then press F3, and that's going to mark the minimum for me as being at 2.33. That's the lower point. So press execute to mark that point. Then you can press exit, regraph it, so that you see just the points you were really wanting to analyze. You've got your endpoints, and you've got your point where the derivative would have been 0, and you can compare this to get this to be your minimum value and that to be your maximum value. We're about through for the night, and the only last slide I have to show you that I'm not going to do anything with integration night, as tempting as it is. I love the integration features, the way you can explore area and different values like that. But I just wanted to tell you, if you haven't explored area with your Prism calculator, you need to find a webinar and go see that. The last screenshot is one that just basically shows you the email address for all the Casio Education resources that you can go to. If you go to that website, they've got some online training courses that you can go through that lead you through many of the different modules that are in the calculator program. And if you complete that program, as of right now, you can have access to one of the Prism emulators. I appreciate you sticking with me tonight, and hope that you have a great year. Thank you.
Hey, Dee Dee, thank you very much, and thank you for mentioning the online course. I think one of the things you did this evening that I enjoyed was the using the derivative of y1. I think that's an underutilized function or functionality where you can change y1 and you're automatically looking at the derivative.
Right.
So thanks for pointing that out. Thanks to all who have joined us, and we have been recording this, and we are going to be sure to post it within the next week or two. We have a YouTube channel, and we will also be posting a link to that on our website, thiscasioeducation.com. So thanks again, and everybody have a good evening.